right? So orbital diagram and SPDF notation shows how the electrons are distributed among the various atomic orbitals. So we can denote the electronic configuration by using two ways. The first one is called the SPDF notation, and the second one is called the orbital diagram. So when it comes to diagram, that means you have to draw, right? So for example, this is for SPDF notation. So in SPDF notation, the electronic configuration is denoted by writing the symbol for the occupied orbital and adding a subscript to indicate the number of electrons in that orbital. Okay, for example, we can see that helium contains of 2 protons. That means helium atom contains of 2 electrons as well. So this is how we write the SPDF notation for helium. That means these 2 electrons, we are going to fill it up into 1s orbitals. So helium equal to 1s2 superscript, right? Please make sure it is written as superscript. So 1 represents the principal quantum number, and meanwhile S represents its azimuthal quantum number L, and 2 represent the number of electrons in the 1s orbital. Okay, so remember, this is superscript. You can't write S1, S2. It's very wrong. Okay, so you need to write 1 as superscript 2, right? Meanwhile, for orbital diagram, each orbital is represented by a box and each electron by an arrow. And an arrow used here, okay, you should use what? We call half-headed arrow. Okay, you can't draw a full-headed arrow. Okay, please draw half-headed arrow. For example, lithium has 3 electrons, has the orbital diagram as follows. Okay, so if, for example, for 3 lithium, SPDF notation for 3 lithium is 1s2, 2s1. Next, you have to draw the orbital diagram for it. So that means just draw a line, okay, and then show these 2 electrons are spinning in the opposite directions, and please use half-headed arrow. Okay, don't use like this. This is what I call full-headed arrow. So you can't use this. You must use the half-headed arrow pointing in opposite direction. And 1s in 2s orbital consists of 1 electron. So fill in this. Okay, fill in the electron. Draw the electron. Okay, like this. Okay, next. Okay, so this is just an explanation. It says that the arrowhead indicate the direction of spin. So arrow pointing the upward, okay, represent an electron with, okay, positive quantum spin quantum number as equal to positive half. Meanwhile, arrow pointing downward, okay, represent negative spin quantum number as equal to negative half. Okay. So these are some exercises that you need to try to do. So for oxygen we have done it, and then for neon, nitrogen, and also for fluorine. So this is the answer. So first, since oxygen have 8 electrons, so those electrons are going to be filled up into 1s2, 2s2, 2p4. So you can count the number of electrons, 2 plus 2 plus 4. So there are 8 electrons, right? So this is the orbital diagram. Okay, you don't have to draw boxes, just draw lines as we did before. Okay, next for neon, since neon consists of 10 electrons, okay, so 2 electrons in the 1s orbital, 2 electrons in the 2s orbital, meanwhile 6 electrons in the 2p orbitals. For nitrogen, consists of 7 electrons, okay, so 2 electrons will be in 1s, 2 electrons in 2s orbital, and 3 electrons in the 2p orbitals. Meanwhile, for fluorine, since it contains of 9 electrons, so 2 electrons will be fit into 1s orbital, 2 electrons into the 2s orbitals, and 5 electrons in the 2p orbital. Okay. Now we are going to look at the electron configuration of ions. So why do we form ions? Right. So main group atoms may lose or gain enough electrons so as to form stable noble gas configuration. Okay. So noble gas is group A, group 18. Right. So the stable noble gas configuration should have NS2 and np6. That means the outermost electron, okay, the valence electron must have this configuration, ns2 np6. So metal elements, okay, metal elements, for example, group 1, 2, and also 13, okay, tend to lose electron, okay, in order to to form this stable noble gas configuration. So that means when it loses electron, it's going to form positive ion, okay, which is called the cation. Right? For example, we have sodium with a proton number of 11. Right? So when it has 11 proton, that means it consists of 11 electrons. So these 11 electrons, okay, will be assigned into 1s, 1s2, 2s2, 2p6, and also 3s1, right? But in order to achieve stability, it needs to have a stable or octet noble gas configuration. Okay, so in order to achieve this configuration, you need to remove this one electrons. So when we remove one electron, it's going to form Na plus. Right? So this is the electronic configuration for Na plus. So now Na plus has already achieved its stable octet configuration. Right, next, non-metal elements, for example, group 15, 16, and 17 tend to gain electrons, right, in order to achieve this stable noble gas configuration. So when it gains electrons, it's going to form negative ion, which is called the anion. Right, for example, we have fluorine with a proton number of 9, so it consists of 9 electrons. So these 9 electrons will be assigned to 1s2, 2s2, 2p5. So in order to achieve stable noble gas configuration, it needs to add one more electron into the 2p orbitals. So that means fluorine is going to accept one more of electron, forming F minus. Therefore, this is the new electronic configuration for F minus, which is equal to the electronic configuration of neon. Okay, neon is an element from group 18, which is the noble gas. Okay, noble gas group. Therefore, remember, atoms tend to lose or accept electron in order to achieve the stable noble gas configuration or the stable octet configuration. Okay. So, okay, remember, when we want to form monoatomic ions, for example, cation, so we need to remove electrons. So how are we going to remove electrons? Please make sure the electrons are removed from the orbital of the highest energy and farthest away from nucleus. Yes, because the further the orbital the further the electron from the nucleus, the less attraction that the electron feel. Therefore, when we want to form cation, we have to remove electrons. So which electron are you going to remove? Please remove the one with the highest energy and farther away from the farthest away from nucleus. For example, we have manganese with 25 number of protons. Okay, so it consists of 25 electrons. Therefore, when you write its electronic configuration in the form of SPDF notation, so this is what it look like. Okay, 4s2 3d 3d5. Okay, next, let's say we want to form manganese 2 plus, so that means you have to remove 2 electrons. Okay, so which electrons are you going to remove? Okay, remember, we are going to remove the outermost electrons. Okay, so the outermost electron is not from 3d but is from the outermost shell, which is the 4s. So when we need to form a manganese 2 plus, you need to remove 2 electrons. So you have to remove electrons from 4s orbitals. So finally, its electronic configuration will be 1s2, 2s2, 2p6, 3s2, 3p6, and also 3d, 3d5. Okay. Next, for manganese 3 plus, okay, that means you have to remove 3 electrons. So 2 electrons will be removed from the 4s orbitals, and then another electron will be removed from 3d, making it become 3d, 3d4. Okay. So meanwhile, when you add electron, when you form an ion, you have to add electron. So please add electron to the orbital of the highest energy and also the farthest away from the nucleus. For example, 17 chlorine. Okay, this is the chlorine atom. Okay, so in order to form a stable noble gas configuration, you just need one more electron. So the extra electron will be added to the 3p orbital so that it will achieve a stable noble gas configuration. Okay, so this is magnesium. You need to produce magnesium 2 plus. We have to remove electron from the 3s orbitals. Okay, so this is fluorine, consists of 9 electrons. So you have to accept one more electron, okay, to achieve the stable noble gas configuration. Okay, so first you must draw, okay, the SPTF notation, the orbital diagram. Next, write up the SPTF notation, and then in order to form Ti2 plus, you need to remove the outermost electron, which is from the 4s orbital. Okay, so now the anomalies electronic configuration of chromium and copper. So just these two elements have anomalies. Okay, so chromium, how many electron number are there? There are 24. Meanwhile, for copper, there are 29. 29 electrons. Okay, so we call anomalous. Anomalous means what? Inconsistent. Okay, not normal. So copper and chromium have electronic configuration which are inconsistent with the Aufbau principle. Okay, remember Aufbau principle said that okay, we must fill in the orbital with the lowest energy first, right? Before moving up. But then here there are anomalies when we fill the electron into orbitals for chromium and copper. So these anomalies are explained based on the basis that a fully filled or half-filled orbital is more stable. So let's look at the example. So when you answer the anomalous case, please draw it like this. Okay, please answer it like this. First, you must say expected configuration. So if we follow the Aufbau, principle, okay, we must fill into the lowest energy orbital first. Right, so since chromium consists of 24 electrons, so 2 plus 2 plus 6, so here already 10 electrons. Next, okay, up to this also 10 electrons. So now you still have 4 electrons remaining. So if you follow the Aufbau rule, okay, you tend to fill in the 4s2 orbital and then 3d, 3d4. But okay, 4s2, 3d4. But now actual configuration is actually 4s1, 3d5, right? Depan ni semua sama, tak ada masalah. Just the difference is here. Okay, is here. So why? Okay, you must justify. So first you must write down the expected configuration. The second one you must write down the actual configuration and then explain. So the explanation is one electron in the 4s subshell is promoted to occupy partially 3d subshell. Okay, why? Because due to the stability of the half fill, okay, we can see that the actual configuration we have the half filled 3d orbital because remember 3d can fit up to 10 electrons. So when we fill the 3d orbital up to 5, that's mean okay, we form okay the half filled 3d orbital which is more stable compared to this one. Therefore you must answer okay, one shell in the 4s subshell is permitted to occupy okay, partially 3d subshell. Okay, so This is due to the stability of the half-filled 3D subshell. Therefore, you can see 3D half-filled 3D subshell is more stable. The keyword is stability of the half-filled 3D subshell. Okay. Meanwhile, as for copper, since it contains of 29 electrons, so you can expect that expected configuration is 4s2 3d9, but this is not the case. Actual configuration will be 4s1 3d10. So for the same reason, one electron from the 4s orbital is promoted to occupy fully 3d subshell. This is because due to the stability of the completely filled 3D subshell. So remember, there are three types of stability. The first one is noble gas configuration, which is stable. The second one is called the half-filled orbital stability, which is for d orbitals. So when we have d orbitals, when the d orbitals is filled with 5 electrons, so that is considered stable. Meanwhile, another type of stability is called completely filled. Completely filled orbital. For example, for copper, it contains of 10 electrons in the 3D subshell, so that means this is very stable. So instead of forming 3D9, it tend to form 3D10.